Yeah, good morning my dear students. Today I am going to discuss about the various deviations of Beer-Lambert's law, as well as I am going to discuss about the effects of solvents in UV visible spectroscopy. So what my session is today, particularly I am focusing on reasons for deviation of Beer-Lambert's law. So when I talk about the reasons of deviation of Beer-Lambert's law, I just make a concentration on x-axis and plotting absorbance on y-axis. So when I plot this, I am getting a straight line which gives the linearity of the straight line. Suppose if the deviation is bending towards more and more on the y-axis, on the positive side, then it is called a positive deviation. If the deviation is more bending towards the negative side, or if it is more towards the x-axis, it is called a negative deviation. So there are two types of deviation possible with Beer-Lambert's law. One is positive deviation, another one is negative deviation. Now, what is the reason? What is the major reason for this deviation? The first important reason is instrumental error. What is this instrumental error? So when I talk about the instrumental error, we have a light source, and then light source is followed by slit. Slit is to control the intensity of light radiation. Then we have the monochromator. Monochromator is used for separating the wavelength of dispersed radiation. After comes your sample cell, then comes your detector. Right? Detector converts the light energy to electrical energy. This is the basic function of any photoelectric detectors. Now this light source, if there is any error in the light source, that will lead to instrumental error. Similarly, if there is any problem in the slit width, the width of the slit, which will control the intensity of radiation, if there is any problem in the slit width, again it will lead to instrumental error. Then comes your monochromator. If the monochromator is not functioning well, it leads to instrumental error. Again, coming to the detector, if the detector is not functioning well, again it will lead to instrumental error. Not only the detector malfunction, also there is a possibility of stray radiation. Stray radiations are the outside radiations which are responsible for affecting the detector. And then some signal noises. Whenever there is a flow of electron, there is always a noise produced in the detector. So always there are some signal noises produced by the detector, which is also a reason for instrumental error. So this is the first primary importance for instrumental error, especially for deviation of Beer-Lambert's law. Now coming to the second important aspect, chemical error. What is this chemical error? Chemical error is concerned with either association of the molecule or dissociation of the molecule. So when I talk about association of the molecule, I just give an example. Methylene blue is existing in monomer form. It is having the lambda max of 660 nanometer, and when it is converted into dimer, it exists as 600 nanometer. So here the concentration will be higher in dimer, 10 power minus 4 moles, whereas in case of monomer, the concentration is little less, that is a 10 power minus 5 moles. So this is an example for association of the molecule. Dissociation of the molecule is also one of the reason for chemical error, where dichromate, potassium dichromate, upon hydrolysis in water, it will be converted into chromate ion as well as hydrogen ion. So this is dichromate is orange in color, which is having the lambda max of 450 nanometer, whereas chromate is yellow in color, having the lambda max of 410 nanometer. So this is an example for dissociation of molecule. Then comes some other phenomena like ionization of the molecule, complexation of the molecule, reaction with the reagents used, as well as pH change, polymerization, and solvation of the molecule. All these factors are responsible for causing the chemical error of Beer-Lambert's law. Now comes other phenomenal effects which is also leading the deviation of Beer-Lambert's law, such as photodegradation of the molecule as well as emission of fluorescence. Our original principle is absorption, but here emission of fluorescence is an unwanted phenomena that also leads to error in your Beer-Lambert's law. Then comes our physical factors. The physical factors, wavelength selection is one of the prominent factor. Then comes your higher concentration. So these two factors are also responsible for deviation of Beer-Lambert's law. Coming to the solvent error, most of the solvents, particularly the aromatic chromophores, whenever we consider about the aromatic chromophores always try to give the fine structures of vibration in the non-polar solvents. So whenever you are using any aromatic molecule, you try to always prefer to use the organic polar solvents, which will reduce the vibrational pattern, and therefore you will be getting the proper spectra for your molecule. Otherwise, if you are using aromatic chromophores, if you are using this non-polar solvents, it is a disadvantage and it will lead to more and more solvent error. And the last one more example is use the distilled water if you are using a single distilled water or double distilled water, that will be more preferable for getting the proper reading in UV visible spectrophotometry. Otherwise, if you are using deionized water, that leads to some ion exchange resins, and that are always a problem for causing deviation in Beer-Lambert's law. So this is all about the various reasons for deviation of Beer-Lambert's law, and particularly we are going to discuss in detail about the solvent effects in UV visible spectroscopy. So what is this solvent effect? When we are talking about the solvent effect, each solvent is having the lower cutoff wavelength region. When we are discussing about the solvent, every solvent they are having a fixed lower cutoff wavelength region. Below this range, the solvent cannot be used. Suppose I will give an example here. Below that range, you cannot use that particular solvent. For example, the polar substance will be dissolved in polar solvents, like dissolves like. Similarly, non-polar solutes will be dissolved in non-polar solvents. And as I told, if you are using any solvent, the cutoff wavelength will be given, lower cutoff wavelength is given. If you are using below that range, definitely there will be a stray radiation effect, and that leads to disturbance in the Beer-Lambert's law as such, right? So undissolved particles, if at all, if you are not using the solvent, proper solvent, and if your sample is not dissolved properly, what will happen? Instead of absorption, there is an unwanted scattering of light radiation takes place, which is an unwanted phenomena. Right? So polar solvents are better because they wipe out the vibrational patterns, right? So polar solvents are always preferable, and colorless solvents are preferable for the visible region. When we are using the visible region like colorimetry, we try to better go for using colorless solvents so that the color will not be interfere with the sample, right? These are the example for the common UV solvents under lower cutoff wavelength region. So acetone is having 331 nanometer, pyridine is having 306 nanometer, toluene 285 nanometer, carbon tetrachloride 265 nanometer. So every solvents are having the lower cutoff wavelength region. Okay. Now for example, if we are using aspirin, for example, if I am using aspirin here, aspirin is 299 nanometer. For example, the substance aspirin, I have to measure the sample in 299 nanometer. This is the sample wavelength where I have to measure the absorbance. Now what may be the solvent I have to use it? The solvent, whatever I am using, that should not be less than 299 nanometer. That means I have to use either acetone or pyridine. These solvents I have to use it, right? Suppose this is my wavelength for the sample. If I use the solvent of chloroform, for example, chloroform is 245 nanometer. So in this case, what will happen? Below the lower cutoff wavelength region, so this solvent will not be, or this solvent will not be a better solvent as such. That means what you have to do, whenever you choose the solvent should be used in such a manner that it is having the lower cutoff wavelength region. Below that region, you should not use any other solvent as such. If the wavelength region is 306 nanometer, below that region, you cannot use pyridine as a solvent. Okay, so that is a very, very important criteria one must use for choosing the right solvent for doing UV visible spectrophotometry. Now, coming to this, one cannot use this as a solvent. As I told already, when I dissolve the sample in non-polar solvent like hexane, and another same sample I am dissolving in polar solvent like alcohol. Now, what I mean to say, the decreased absorption maximum, right? And you have an increased absorption maximum. Why we have a decreased absorption maximum? When you dissolve the sample in non-polar solvent, you have a decreased absorption maximum, that is a decreased lambda max. Whereas in case of polar solvent, you will having an increased absorption maximum where you have an increased lambda max. So what type of things we are getting? The red shift, particularly pi to pi star transition is taking place in the molecule. This is a clear indication that there is a possibility of a bathochromic shift or red shift taking place in the molecule, pi to pi star transition taking place in the molecule, right? So for this thing, exception is certain compounds like dienes and other hydrocarbon polyenes. These are all some of the exceptions. You may not get the bathochromic shift. Some cases, if you look at that, both N to pi star transition and N to sigma star transitions are blue shifted by hydrogen bonding solvents. This is also another important effect. So we have discussed the N to pi star transition and the N to sigma star transitions. So they are basically blue shifted. That means they will go for hypsochromic shift, right? By the hydrogen bonding solvents. So when you use the hydrogen bonding solvents, like for example, alcohol, CH3OH, right? The hydrogen with the hydroxyl group, where it is having a hydrogen bonding effect. So such type of solvents when we are using, so N to pi star transition and N to sigma star transitions will try to preferably go for hypsochromic shift, that is decrease in lambda max. So pi to pi star transitions absorb 10 times greater than or more strongly than the N to pi star transitions. This is also very important fact. Whenever you go for pi to pi star transitions, they always absorb 10 times greater than or more strongly than N to pi star transitions. So this is all with related to the effect of solvent. So say for example, your substance may be dissolved in all the solvents, but which solvent you have to choose for UV visible spectroscopy, that is very important, depending upon the lower cutoff wavelength region. If your solvent is having a particular lower cutoff wavelength region, below that region you should not use that particular solvent. This is very important, because say aspirin I am using 299 nanometer. So below that region you should not use these as a solvent. Even though aspirin is dissolved in all the solvents, we cannot use all these solvents as such. So which is the solvent I can use it? So 306 nanometer and 330 nanometer. Either I can use acetone or I can use pyridine. The rest of the solvents I am not preferring to use for aspirin. This is the general idea one should think when we go for discussing about the solvent effect. So this is all about the various aspects of reasons for deviation of Beer-Lambert's law, as well as the solvent effect on UV visible spectroscopy. So thank you very much. Thank you, dear students.